60%, and in some cases greater. So what does that mean? I can take concrete. So when they pour this slab, typically it's going to have rebar in it. When they make streets or sidewalks or anything, rebar and concrete. If I can reduce the amount of material in that slab, I've saved all those transportation costs, I've saved all that weight, all that mass in the manufacturing, etc. Same holds true for buildings. Can you save 30 to 60% of the weight of the building? These are dramatic. In the structural engineering environment, if you can save 10% of anything, that's a huge number. Even 5%, particularly if you're talking about a jetliner, where weight is critical, getting that thing off the ground. If you can save 5%, the fuel savings add up significantly. So when we look at materials, and I maintain I can save 30 to 60% of the mass of the material, we can build then common structural forms that we're all familiar with. And so what are those? You go to Home Depot. What do you buy? You buy 2x4s. You buy dimensional lumbers of all kinds. You buy I-beams of certain dimensions. You buy blocks of materials. And these are all the things that the carpenters and welders, and they wouldn't buy it necessarily from Home Depot. But they start with traditional form factors, plates of metal, blocks of something. They go on to lathes and they get manufactured and put into other products, and we don't see that stuff. But that's how they start out, as the basic form factors from which other things are derived. And the materials have intrinsic properties such as porosity, anisotropy. Are anyone familiar with this chemical term? I don't pronounce it correctly. It's anisotropic, but basically it means that something can vary along all three axes independently of one another. So I can make this material over here different from the material over here. I can do that by changing the elastic properties of the material. And so we think of elasticity like this. So here's the same thing. I'll pass that around. There's the same thing. And all I've done there is change the interconnecting element. And that interconnecting element is acting in tension, and the icosahedron is acting in compression. And so we get a tremendous reduction in mass in the material, and it turns out that that's the sweet spot. That's where everybody wants to be. And that's strength over mass. And so you can see on a chart here, your foams are down here, which of course have not much strength, but they're very light, right? So you want to be very light and very strong. By the way, I've got a few of these to take home, if anybody wants to take them. They serve no purpose other than they've got some little cute little faces on them. And they hold down paper on your desk. That's about all they're good for. Some of the other properties that I talked about, you can see that it's inherently open. So we've spent a great deal of time in the modern materials by trying to get things closer and closer together. And I maintain this is exactly the wrong approach. What we want to do is space them apart. And that's what this allows us to do, is have this open architecture. So they become permeable. And why is this important? Well, the city of Portland just spent $1.5 billion putting in the west side pipe and east side pipe. You probably have all heard about that. And now they pump all this stuff over to the wastewater treatment out there in the Columbia Slough. So that's $1.5 billion. If you had permeable surfaces on your sidewalks and on your streets, then all of that would flow down into the ground, as a naturally regenerative environment does. I spoke about anisotropy, so you could have some of those materials, like the one you're holding, or the red one, so it could be stiff in one location and flexible in another location. Now, why would that be interesting to us? We could have a a manufactured sidewalk that's very comfortable to walk on. It's cushioning, right? But when we get to the curb where the car is going to run up on the curb, we want something that's stiffer. So we could use the same material, and just by varying the properties within the material, we can have different effects that we're trying to achieve. Now, I want you to keep in mind, all of these things are of a certain size because these are easy to manufacture. If it's very small, I can't get my hands around it. So all of this is injection molding, and it's just simply for demonstration purposes.
So these are all plastic, but it could be other substances.
Here's an example where it's in stainless steel.
What else could it be?
Well, it could be mixed materials. Here's a plastic and steel. We're only limited by our imagination. So these could be made out of wood. The interconnecting elements could be made out of bamboo, for example. So when there's this quiz I was telling you about at the end of the presentation, I want to get your ideas on all of this. So the material is independent of scale, so it can be very small. So the patents that I have on this material cover the nanoscale, so that's 10 to the minus 9, because it's the same stuff. So it can be very, very large or very, very small. And it's independent of the material from which it is derived. So it's just geometry. That's all this is, just geometry. Okay, I spoke earlier about how stable the triangle is. The icosahedron is made from 20 equilateral faces, all comprised of triangles. I'm just going to back up a little bit and tell you about the history of how I came to develop these structures. I went off and did software for a long time and had a company down in Corvallis that was successful and ended up selling that. And that was a lot of work. And I don't ever want to work that hard again in my life. But then I went on and did other things, but I found myself 6 or 7 years ago wondering what I'm going to do with the rest of my life. And this had always been a passion of mine, going back many, many years. And I knew from that work that I showed you earlier that there was some basic geometry that just needed to come out. And I wasn't sure what it was, but I had a pretty good idea what direction to go in. So I built one of these tensegrity structures that I was showing you much earlier. And this is what's in the textbooks, if you will. So if you go back and read Fuller, you're going to find a lot of these structures in Fuller. And they are basically comprised of dowels and wires. And if you look at Kenneth Snelson's, the artist that I was mentioning, his work is largely the replacement of these dowels with stainless steel dowels and beefier wires. But essentially the same stuff. But when I built one, I immediately realized, after my years in the darkroom, and I don't know if darkrooms are almost becoming passé. This generation doesn't have any experience with darkrooms, do you? That when you expose the negative onto the paper and then you put it into the solution, what was white then becomes black, and that's how you get the shadows and the contours and all of that. And so when I was looking at this structure, I suddenly realized I was looking at it the wrong way. It should be where the dowels were in compression, they should be in tension, and these icosahedrons are formed by the wires. And so if I just simply reversed how this structure was put together, I could get to this right here. And so that's essentially what this is. This is that structure executed in stainless steel. Now, I want to show you some other aspects of this, because this will fool you. Remember, we were talking about the building here. And the building is in compression, and these beams are in tension. They're actually being bowed a little bit. It's infinitesimal, but if you put a laser system on it, you could actually detect that. So if you take this structure, and notice these are the tension bands right here. See that? They're in tension. And if I put a load on that, What am I doing? I'm loading the tension. Well, that's all wrong. I don't want to load tension. I want to pull tension, right? So that's all wrong. So what you have to do is you take this whole structure and you rotate everything, all three axes, 45 degrees. So here we are, the same structure, and it's loaded from the top, and all the tension is vertical. Okay, but we're going to take it and we're just going to rotate it, all three axes, and now all of the loading happens on the icosahedrons, and the tension is what's holding it together. So that becomes a central clue in how all of this is held together. Did everybody get that, or is this too far away? Not that. So the icosahedron, it turns out, is a very important structure. It has what's called five-fold symmetry, which is very unique, which means to say that I can take it, I can hold it on its axis, and I can rotate it through 72 degrees 5 times. 5 times 72 is 360 degrees, and it gets a mirror image of itself every time I go through 72 degrees. It's the same structure. So it's the same structure. So it lends itself perfectly to these interconnecting elements. There are just a few other naturally occurring five-fold symmetry structures. One of them happens to be a truncated icosahedron, which in the modern lexicography is a fullerene. Now, some of you are probably familiar with fullerenes, which is a very, very small structure. And down near the nanoscale, but not quite. So here's the first paper model of this. Do everything out of paper. And so here are the 6 planes. So if we go back to here, we have 6 planes. And we divide each one of these planes. So this is a plane, right, like that. So there's 6 planes that bound this. And we divide each plane into 2, so we get 12. We get 12 interconnecting elements. And so it turns out that this central icosahedron in there, this is the basic cell. The central icosahedron is held, or suspended in this case, by 12 interconnecting elements. And that is what constrains the 12 degrees of freedom. So the 6 degrees of freedom are up, down, left, right, right. If you're trying to, you got your buddy, grab him, don't let him get away, right? That's what you got. The guy can go up, down, he can go forward or back, left and right. But as it turns out, if you have volume, so I can still twist like that. Terry plays down. So you can still twist. So if you're trying to constrain twisting and rotation of that, it takes 12 elements to constrain that. So once that constrained, then this one cell, this next icosahedron, becomes the central organizing cell for the next 12 and the next 12. So this is the basic cell that expands ad infinitum. And it does that in this tensile network that's been rotated 45 degrees on all 3 axes. And then you add the compressive element in there. And then you get arrays. And once you make an array, you can make virtually any form factor. So anything you can dream up, you can make out of this stuff. Has some very unique properties. The way a load is distributed through it. And if you think about a 2x4, so here we have a representation of a 4x4 oak beam. But if you think about the cellular network of that 4x4 and what's happening when you load it, it's going to fracture. What's binding all those cells together is the dried out lignin that originally held that tree together, right? And it dries out, and that's what's holding that cellular network together. But it doesn't, it's very brittle when you think about it. So when we load these structures then, that load is distributed throughout all the layers, and it's diminishing as that load is distributed. So if you have a truck tire going across it, you get a visualization of how that load is being distributed across it if you're building a bridge, etc. I'm going to get into discuss a little bit of math because this is where we're at now. I was giving you a representation, so we have basically a pretty small subset of this whole thing, approximately like this. And it turns out to be about 112 icosahedron. And we've written over 33,000 lines of code right now. What we're trying to do is be able to analyze the behavior of this material in a virtual space on a computer so that we can begin to load it with the loads that a structural engineer might commonly have to deal with, or an industrial designer. Again, we can make all the same form factors. I kind of skipped around. It seems like there was a slide missing. So what I wanted to just close with this statement here was we've done some preliminary analysis. This turns out to be, we're executing about 1,250 differential, here we go, 1,274 differential, these are called ordinary differential expressions simultaneously, just for a relatively small chunk of this stuff. So when you think about the computational power necessary to build this in a virtual space, it gets very large very quickly, and it's created a lot of problems for us. So these are the traditional form factors. These are some of the properties of the materials. We already talked about the permeability. We talked about a concept for a sidewalk. It's omni-extensible, right? It doesn't make any difference. You can build it in all directions. Scalable, so here's a C60, that's the fullerene, carbon-60 molecule, probably about 10 to the minus 7. You can put it into a sidewalk, you can scale it up and put it into an apartment complex, and that has some natural advantages because then you can control the elastic properties of it. So if you're in a seismic zone and the building is shaking, it's not going to break apart at the joints, it's going to just sway and resonate. We talked about anistrophy, but in this case you can just think of it in terms of layers. So if you were in Boston, for example, or even Portland, you might have a heated layer. You might have, well, that would be your heated layer. You might have a traction layer, so it would have a different consistency about it. Might even have embedded advertising. Everything has a known location. Beth, you were raising the idea of a NASCAR race barrier. So you could build resilient surfaces for high impact. So if a car hits this, it's going to deform locally, but those forces will be spread everywhere. You can make it very flexible. So this is essentially this material here. This is a much bigger representation. It was just folded over onto itself. Exactly the same stuff. Has a very high surface area to volume. So this polyhedra, remember I was talking about the platonic solids, tetrahedron, octahedron, dodecahedron, etc. This is the closest approximation to the sphere, and as you know, the sphere has a maximum surface area, minimum surface area for the maximum amount of volume. So that's precisely what this has. So if you wanted to coat this for reactive surfaces, that would be a good route to go. Everything has a known location. So that becomes very important if you're doing microcomputing and you want to put an electrical charge in a known location. You would know where it is on an XYZ axis. So we go back to the sidewalk example. Suppose you wanted to the retailer wanted to put advertising on the sidewalk. And so you could light up the sidewalk, and he could change the display, but it would have a known location, so it would have just very much like your television set. Talked a little bit about stress over strain, but you could take all the traditional form factors that I've described. In this case, you take an I-beam, and you could make an I-beam so you have a microstructure within the macrostructure of the I-beam. And there it is. All built with, this is version 3. That's what it's called. Here's a concept of an artificial reef. You could have, you create a little fish habitat where small fish hide from big fish, right? Isn't that what a coral reef is? Part of it is just a defensive environment. They can find their little way and get away from that big fish that wants to eat them. But at the same time, you're stabilizing the shoreline. So you could develop processes where you'd be assembling the stuff off the backs of ships and laying it down like a mat. And you could make this out of an iron. Many of you might know that in the oceans, a lot of the ocean it's not necessarily a dead zone, but they lack the kinds of fecundity. There's not the basic ingredients. And one of the limited element in much of the ocean is iron. And so we could seed parts of the ocean with iron, and that would bring more life back to it. So you start off with the little copepods, the little sea cows. That's what they are. They're called. And then they're small, they're microscopic, and then they get eaten by the sardines and so on and so forth. And then you could build a nice habitat. So you could have here taking a very conventional structure, like a traditional house. You have rafters and all of that. You could weave the house. So you weave it with all the same material. Or if you didn't want to go that far with it, you could weave a safe room within that house. So here's a seismically stable office tower. Again, the structure is going to resonate. Biomaterials, everything has a known location, so maybe use it for muscle replacement. So you could have a little microprocessor, and it might cause it to contract or expand. Because it has a large surface area to volume, you could use it as a heat sink. You coat it with reactive materials for catalytic converters. And this illustration is actually this stuff. There's a number of ways of making this stuff, and with each passing way of doing it, here. What happened to that? Oh, here it is. So, as you look at that, you'll note that there's 6 gray elements there. So we were thinking very hard about how would you go into mass production. Well, could you just take these 6 and make that as a single injection molded piece, right? Rather than dealing with the individual 6, and then, oh, here it is. And then, rather than having all these little wires and things, make that your tensile component. So this is your compressive component, and there's an injection molded. All your tensile elements that are represented in this upper half are then injection molded as one piece. So you've eliminated 6 of these into one, and you've eliminated, I think it's 13 tensile elements. You made it into one piece. And then you could just roll the stuff off you've got your gloppita machine going, you know, it's just spitting it out, and then it's all being assembled in some kind of conveyor system. It's coming out the other end, and you end up with something that looks like that. It doesn't have to look like this. It's just, that's just the first cut at it. This is not typically where I want to go, military applications. It's regrettable that that's part of our daily lives, but this might make a very good protective armor. And you could make this out of ceramic and make it very lightweight. Decorative lighting features. I've been speaking more to these kinds of applications, civil engineering applications, retaining wall drainage systems, pipe supports. So as you know, there's a lot of debate going on about how we're going to get the last remaining few drops of oil from Alaska. I know we could try to stop it, but it's not going to happen that way. They're going to build a parallel pipeline. That's just it's almost inevitable. But rather than build concrete structures to support the pipe, you could build bio-friendly kinds of structures that just sit on top of the tundra. And then and there are a lot of quakes in Alaska, if there's a vibration, the pipe's not going to break. Right? The whole thing will kind of bend and give with the earthquake. Here's a depiction of how you might, buildings in earthquakes, because of their different size and different mass, sway at different periods, and then they collide against each other. And that's what causes them to break apart. Well, you could pick up a lot of that resonance and dissipate it within these kinds of structures. Expansion joints, crash barriers we talked about. We talked about smart sidewalks. Here's a civil engineering construction, making a whole bridge, earth embankments, earth stabilization projects. These things are going on all around us today. And they're enormously expensive, and they're getting much more expensive. And when we start talking about infrastructure and replacing or repairing, rehabilitating our existing infrastructure, we'll probably have to go to structures like this that we can envision where these might be painted on. Literally paint them over existing structures. And don't think of painting as we think of sort of rolling things on today, but it might be where you stick some kind of gooey mass up and you polarize it from either end. So you've got a positive and negative, and the geometry within it aligns like this. We just provided the basic ingredients, and now you've caused. So these icosahedrons might have a positive charge on it, and the electromagnetic or the interconnecting element might be a negative one, and then you give it sufficient charge that they bind together and they assemble themselves into this array that surrounds the existing deteriorating infrastructure and gives it another 100 years of life. It's just a concept. There's a quiz at the end of this. I want you to come up with big ideas. So, there is a conclusion. You're lucky. It's a new class of structurally optimized materials that has unique properties not found in existing materials. We can reduce the mass of comparable materials with the same strength characteristics. And everything that I've talked about is available on my website. That's it. Thank you. And there's also a book. If you'd like to see that, that's also available on Amazon.com. I want to hear your ideas. What you saw basically, these are all prototypes. Those were some of the ideas that I've come up with. But what I'm looking for is the pet rock. I want to know that killer application that'll introduce this product to humanity.
Is there a way you could perhaps create a framework something that would be biodegradable but would be replaced by a natural framework that would grow through it as it biodegraded, maybe. Something like that.
Excellent.
Like a turf or something like that.
Excellent. So, so anything in tension. What's in tension? A vine is in tension, right? And there's kudzu. Think about kudzu. Now, there's a strong vine for you. So we could grow it in a greenhouse, and we could cause it to basically follow this pattern, and we could make these out of bamboo. And the idea being that you'd have maybe a retaining wall or something like that that would biodegrade over time, but it would seed itself for the next generation. So contained in the icosahedron may be the macronutrients for the next generation.
Is there a way to bind form like that without using physical tension components, but magnetic or electromagnetic tension components, like increase the electricity and everything sucks together, but it can only suck together so far because it has opposing magnets or something like that?
Well, you're absolutely right. There might be physical limitations, so it connects,
yeah.
But by virtue of that's as far as it's going to go.
But then it's like completely permeable because there's no actual physical tension component, maybe?
Yeah. My understanding of electrodynamics is small compared to where it needs to be able to. But we're certainly on that wavelength. Trevor, you've got some ideas, I know.
I do.
A veritable fountain of ideas.
I have a question for you, and that center model is that one there. If the top three clear were rotated such that they were above the ones at the base, can you still make the same arrays?
No.
Okay.
No, that would be close packing.
Yes. Yes.
And that's what makes this unique.
And I also was wondering for the icosos, have you made any models where instead of it being more spherical, have you elonged it like an egg? So the say the top and the bottom triangles were the same, the triangles around it were stretched. You would lose some things, but you might also gain some things.
So it would be a polytope of sort, and you would gain orientation. So in other words, wherever the applied load is coming from, you'd want to orient it to that applied load. What you lose, though, is the symmetry of the icosahedron. So if you were talking about mass producing these, and you got the gloppita machine, and then you have to have a machine specifically designed to make sure that this icosahedron is in the polytope is in the right orientation. It's going to fit just right. But you can do away with that machine, so maybe it's another 150,000 in that problem. But what's 150,000? Well, I mean, these things lend themselves to large industrial manufacturing processes, and so $2 to $10 million investments for plants that would spit this out would be nothing. And in an industrial scale, that's not a great deal of money. It really isn't. You think about things like just concrete. Concrete is enormously energy intensive. Most of you know that when they're burning the lime, so if you don't have to make that much concrete, then you've saved a lot of money right there. But it very expensive was what I'm trying to say. Big plants, even things that I had a buddy who built a stud mill. I mean, who would? No, it's got nothing to do with male of the species. These are 2x4s, right? Up in Chehalis. And because they can take relatively small stands of alder now. But these are $10 million investments for just a modest stud mill to make these that are fully automated and have 10 workers in them. Logs go in and 2x4s come out.
How limited is the strength by the connective material? You know, I can see that themselves are very strong, but if it's held together with something stretchy, and that stretchy degrades, that doesn't do as much good.
Well, that's a great question, and that's what we're working on right now. So things are measured. So what you're dealing with is a property called elasticity. And elasticity defines the world in which we live. So steels, and this is what they do to determine elasticities, they take common steels, so maybe you added nickel to it, maybe you got a stainless steel now, and they give it a common form factor, and they literally have presses that just pull it apart. And how much that stretches gives you the modulus of elasticity. Okay, that's stress over strain is the modulus of elasticity. It's a very important number to know. The other important number to know is when does it break? Not just how much is it going to stretch, but when does it break? And so that's what we're attempting to do in this virtual environment that's taken us so long to get there. So that we can, because part of the design cycle, this is injection molding, right? This is all plastic. Why is it plastic? Because plastic is well understood. The injection molding processes have been around for a long time. This is easy substances to work with. So I work with a design guy here in the West Hills, and he works this up in what's called a parametric modeling environment, which means basically everything's got to fit. The system doesn't allow it not to fit. And then literally with the press of a button, it's just computers. It goes to China. Why China? Because everything I'm doing is throwaway. In other words, I'll make 5,000 of these, and then the mold is no good. The problem is in the United States, and I'm not bashing anybody here, the problem in the United States is everything is production ready. So the molds end up costing me 2 or 3 times as much here in this country. Over in China, they're still doing it the old way. So I can get things done a lot less expensively. And then it comes over by container. Where was so injection molding. So as soon as we know what the product is, I'm looking for the product, guys. Still waiting. Then we'll bring it on shore. We'll do everything here in the U.S.
Wheels that have tires built in.
Tires.
Wheel tire. So you got different traction surfaces. You've got everything built in. You can control the parts that are elastic. Control what's stiff. Very long term, you conventionally have, since there's so much surface area, you have battery. So you have a wheel that is the tire, that is the wheel, that is the battery, and also the motor all at once, because you can combine the different elements, you basically got wheels for an entire car now built into a wheel. Everything's sustainable, replaceable, all wheel-based. You start with just the wheel and tire combination.
Were you talking about sailing a minute ago?
Sailing.
Were you earlier before we started?
Sailing is one of my passions, yeah.
Why don't you make a mast or sail? Make it, you have that, your masses would have to be very, very small, and so make a fabric out of it to prove its multi-dimensional strength. Make a mast out of it, and then find dense contract and get drunk.
Let me finish with yours. I think if you use this as the armature, so basically this would be your winding and the armature. So it's surrounding us, so it's creating an electromagnetic current, and then your battery might be elsewhere, but that's definitely one application. So sails, strangely enough, I was out pricing a sail because my Genoa, that's the sail in the front, is torn. And these are not inexpensive items, by the way. They're actually molded now. So they take the basic elements. So when we think about solar arrays, right, they have a uniform surface. And so most of those photons are hitting that panel and glancing off. Right? But we're trying to capture the energy of all those photons, regardless of the sun's transit in the sky. So if we had a coarse surface at the micro level, so this is a nanoscale, and it's a coarse surface, what would happen to a photon is it hits here, for example, and then bounces in there, and then bounces further into the structure. And so you're capturing all of that energy from that photon. I'll call you when I make my first billion. I'll give you a call. I'll probably give you everybody a job.
What would you do if you start your Kickstarter and then 2 weeks later you've got your $7 million? What would you do?
That's what I'm asking you. I don't know what that application is. I really just don't know where to start.
Have you thought about fabric, just in general fabric?
Yeah.
Ripstop, tinted fabric, let's say, or
beat Gore-Tex at their own game.
yeah.
You know,
Permeable, really hard.
Gore-Tex sucks.
Like, what are the things that you're talking about? You're talking about like high surface area, permeability. You got a lot of strength, a lot of different like multiple vector strengths. So I mean, like, what are the products that fit into that profile? I mean, I think fabrics are dynamite. I think the catalytic converter is dynamite. You know, you need a high surface area to react with all the hot gases. Or what did you just say? The solar panels is you know, if you can work out a way that those can actually be you can generate that electricity out of that, whatever this stuff is made.
So I think part of my dilemma is, am I just making incremental improvements, or is it a radical redesign of? So the Army now is spending a lot of effort on what's called intelligent materials. So the material itself might provide a biofeedback to you. Or it might have GPS built into the material. Or it might have some bulletproof characteristics. So you're right, I can do all those things now. I mean, it would be porous, so I could compete with the Gore-Texes of the world. We have those properties, but is it just incremental, or is it going to be a transformative product? I mean,
But if you can,
so good idea.
if you can assign, if each component you can assign a light to it, then it becomes a permeable fabric that's also like a screen, right? Like an LED screen. So you could use that as like permeable water that's also a computer screen. I mean, permeable
Or circuit
fabric.
board even.
Right.
Something like a circuit board, but in multiple dimensions.
Yeah, think about the storage applications for you've got three-dimensional storage capabilities. If you can polarize or give a plus-minus charge to essentially almost molecular level aspects, I mean, you would get orders of magnitude increased storage in the same space, because you say, yeah, X, Y, and Z, you know how to flip that bit. You'd be able to actually you'd be able to create huge storage devices in very small packages.
You were talking about earlier.
Good idea.
Yeah, pneumatic structures.
Yeah.
Have you ever tried to make the central shape like a compressed gas or air? Or would that be possible?
Well, lots of products today are what is called blow molded.
Yeah.
So you just you basically put the substance in there and you inject it with compressed air. Bang! You've got it's a relatively inexpensive way of doing mass producing a lot of products. No, I have not.
Like, or even like 200 psi or 1,000 psi.
That's a lot, right?
Or something.
Yeah.
And then the other thing was, if you had, for instance, if they were really large and you had some kind of span you needed, and it was heat sensitive, expanded or contracted with the temperature, maybe that would have an application where you could heat it or cool it and have it rise or fall on a microbiotic level or something. Or small level.
Trevor, you had an idea. Yeah, you had your hand raised at one point.
If the tensile pieces could attach or detach at will, you could create something that could change shape at like any given moment, right? So one of our previous speakers Sheldon Renan was talking about an intelligent bathtub that would know when someone was slipping and falling and would change its structure to protect the person that's falling, so they're not hitting their body against a hard surface but a soft and malleable surface. So if you had things, the tensile pieces could change their, either it could shift or move or change like how the level of tension so that a surface could be malleable and programmable.
Mm-hmm. Good idea. Good idea. I hadn't thought about people falling in bathtubs, but it is a problem.
Yeah.
We're an aging society.
Mm-hmm.
I am older. I will face this problem. You will face it too. I want to thank everybody for coming here and listening. And wonderful ideas. I'm going to take them home and I'm going to digest them. All of them are good. All of them are good. And love the creativity in this room. Thank you very much. Well, the narcissist in me.
Well, thanks a lot, Sam.
Oh, okay.
So our next Curiosity Club, I don't have the date here. I neglected to write it on the paper, so you can check it. No, that was already happened. So our next Curiosity Club, which you can see on the website, is Eric Vaughn of Box Corporation. It's 2 weeks from today. Eric Vaughn is the founder and CEO of Box Corp, where he takes on the roles of product designer, engineer, and marketeer.
It's the 29th.
It's the 29th of May. He's a 3-time Emmy-nominated visual designer and director. He has 12 issued patents. His studies are in philosophy, logic design, literature, and metaphysics. His invention, the Box electric bike, rated 48 on T3.com's list of the world's hottest gadgets of 2012, and the review was kind of funny, so I thought I'd do it. So, this is from T3.com. On first gaze, it looks like an electric cooker sliced in half and dumped on wheels, but it's actually a super green transportation vessel which will take you up to 80 miles at 35 miles per hour without having to pedal. It charges in an hour and will also support the weight of a 21-stone man. It's a British website. There's a heated seat for those winter commutes, 2-wheel drive, traction control, and anti-lock brakes. It's about the same weight as one Kate Winslet, just as quirky, and takes up less space than the Oscar-winning English Rose. Thanks, everyone.
I have some of these. If anybody wants one of these, I have 5 of them up here.
Yeah.
There we go.
That one? I'll take one.
There you are. One more. Okay, thank you very much.
What's that?
You want one?
Yes.
Okay, there you go.
So here is more.
Oh, I